part of our discussion about satisfiability, we're going to look at propositional satisfiability problems, and these are often called just SAT problems, or SAT for satisfiability. So this is a special case of a constraint satisfaction problem. And the difference is we have Boolean variables, which is a variable with domain true, false. So they're just either a variable either has a value either true or false. And what we're going to do is we're going to write x is true as this atom x, just the lowercase version of that variable x. So x is false, we're going to write it as this value. This is a not symbol, so this is going to read as not x. And you define literal as either an atom or the negation of an atom. So you can see a literal is either an assignment of the variable to be true or an assignment to be false. Then we've got these clausal constraints. So a clause is an expression of the form L1 or L2 or LK, where each Li is a literal and that symbol or means or. So this clause is true if at least one of the Li is true. It's only false if they're all false. And so we're going to use this as a form of clause. And so now we want to find an assignment that satisfies all the constraints, so that makes all of them true. So it's just the same definition we saw before of satisfying constraints. All right. So it turns out it's possible to convert any finite constraint satisfaction into a propositional satisfiability problem. So what we're going to do is a variable with domains v1 to vk, we're going to convert into k Boolean variables. We'll call them y1 to yk, where yi is true when y has value vi and is false otherwise. So that's what here. So y1 is the variable that means that y has value v1, and yk is the variable that's true when big Y has the value vk. And each of these is called an indicator variable. It's either true or false depending on what the value of the variable is. And so what we're going to do is we're going to write the constraints for that. For I is less than j, and maybe we can explain, you can tell us in class why y is less than j is appropriate. What yi and yj can't both be true. And that says that it's not the case that one of them is false. So they can't both be true, so one of them is false. So yi is false or yj is false. And we also know that one of them must be true because y has to have a value, so we have y1 or yk. So that's what we're going to, they're the constraints in here. Then we can think about clauses. So that's the variables and domains. Then we can think of a clause. So one way to think about how to do this is this clause of not xi or not yj or not yk is equivalent to the not of this conjunction. So a disjunction of negative literals is equivalent to the fact we're saying here's some conjunction which is impossible. So one of the ways of representing it as a SAT problem is for every false assignment of values, so we have a set of variables and we have some false assignment, we can represent that as one clause. And what this shows us is that the clausal form can represent any finite constraints. We just have as many clauses as there are false statements in that table. However, we can often do much better than this. We can often do a much more concise description that uses many fewer constraints than this. So this is just an upper bound, but it also shows that we can do all of these things. All right, so now it's interesting because a lot of the algorithms we're going to do have very nice counterparts with satisfiability problems. So what we can do is arc consistency in particular. So we can make arc consistency much more efficient in SAT than we can for general CSPs. So we've made the problem bigger, but now we're going to hope that we can actually solve them faster. Okay. So because the domains are binary, pruning a domain is equivalent to assigning a value to the variable. So when we prune a domain, what we're going to do is instead of having to revisit all these ones because we've assigned a value, we've assigned the value of variables. That's what we're going to think about in here. Is we're going to think about assigning a value of variable, and that's going to happen when we prune a domain in consistency, in arc consistency. Now, if x is assigned to be true, so we've removed x as false, all the clauses with x in it can be removed. They're all satisfied, right? So we've assigned x to be true. Any clause with x in it, we can can remove because they're all satisfied now. So we can now remove lots of, because now we can simplify it. As soon as we have a variable assigned to be true, we can simplify the set of clauses. If x is assigned to be true, right, all the clauses with not x, all the forms of this, where w is the rest of them, we can simplify it to w. We know that x is true, so this is false, so w has to be true. So we're going to keep simplifying the clauses. We're either going to remove them or simplifying the clauses is how we're going to act in here when we actually start assigning values in here. Okay. If we get to a clause with one element, we can assign the corresponding Boolean variable. So if w there is just one element, whether it's true or false, we can now assign that corresponding element and keep going. If all the literals in a clause are removed, there's no solution. That's going to correspond to empty domains. So there's no assignment of these values to literals. And the uniform, the fact that all the constraints are the same and all the variables are basically the same, means we can have very efficient data structures. So we know the domain of every variable. We know it's either unknown or it's true or false. So we know the values of each variable are, they're either, we either know they're true, we know they're false, we don't know them. And all the fact that they're all clauses actually means we can index things very efficiently. So that's one of the reasons why we can solve satisfiability problems are good for consistency algorithms. So it often is the worst that the explosion of what happens in the representation caused by converting to satisfiability can be the fact that we now have a much simpler problem to solve means that it's often the right choice. Let's look at local search. So local search can also be much more efficient for satisfiability problems. So what we're going to do is a complete assignment can be represented just as a bit vector. So now we just have zeros and ones. So now we can represent purely as a bit vector. So now we can represent enormous problems where we might not have been able to represent them before. Although the problems are bigger, we now have more efficient representations for them. And there's now only one alternative value for a variable. So remember, we didn't have to worry about choosing the best value because now there's only one other value for it. So we're now going to just flip the value of a variable whenever we select it. Now, if we change any value in an unsatisfied clause, it becomes clauses satisfied. The only time a clause is unsatisfied is because it's a disjunctive, all of them are false. So as soon as we flip one of them becomes true, so then the clause is true. So if a variable x is changed to be true, all of the clauses containing x become satisfied. So any clause that contains x becomes satisfied. So that's now useful. Only those clauses with not x can become unsatisfied. So we start to check those clauses that contain not x because you have to make sure that that some other variable in them, some other literal in them is true. Okay. And this allows, so now what we can do is we're going to really efficiently index all of the clauses for every variable, we're going to index it into the set of the positive, where it appears positive and where it appears negative. And so now we're going to efficiently index these clauses. We also have an interesting case about the search space is expanded. So before a solution's been found, more than one of the indicator variables could be true. So you could have y1 and y2 could be true, and that means sort of it's the case that we're thinking about the case where y has two values, or all the indicator variables could be false. So considering that maybe y doesn't have any value, but this one here you might think it's rather strange to let a variable have multiple values or a variable have no values, but it expands the search space, and often when we expand the search space, it lets us escape local minima. So as you can see, there are lots and lots of variants of local search algorithms we could possibly do, and people play and try to experiment with different algorithms, different settings, different parameter setting in order to find very efficient ones. But when they do it, it's often the choice we can have as local search with satisfiability is often the choice that people make for solving these problems. Okay, we'll talk about more of this in class. Thank you.